the key point here that is left is how we can design this U, right? Because in this dummy example, we went through the sentence. We see that Julia is important information. We put the gating variable U to be 1. For the next sentence, words in the sentence, we see that they do not have anything special. We set the gate to be 0, right? But in practice, obviously, you cannot do that, right? You need to have a mechanism which is somehow learned or somehow trained from the context itself, right? And the basic idea, as we do always in this course, is to just learn it, right? So you just leave it. You put that functionality inside your model, but you just leave everything inside that tunable, right? And then you try to learn it through training, right? So this is the idea. The idea is that we design something called gate, but we do it exactly the way that we said, with a bunch of parameters which are learnable. For instance, if you have this ht, this is the hidden state at time t minus 1, for example, ht minus 1, and then you want to compute your new hidden state, right? So that hidden state is exactly the memory component we had in our example. How we can do it? We can design this gate, right? We could say that, okay, say x is the input that we have. Then we have this ht minus 1. This is the memory that we had before. Now we're going to just combine them using a bunch of weights, right? This weights wn is the weight of the input. Wm is the weight of the memory. And then you can also add some bias, right? Correct? So if you compute this guy, this is going to be a vector, right? And what you want your gate to be something between 0 and 1, right? That was the idea in the example I gave you, right? 0 means I don't want the information to run out. 1, it means that I want the whole information to pass, right? And then you can pass it through a sigmoid, right? Now, if you put it on data, if you let it learn, then gradually these ways are going to understand this particular input is important. So I'm going to copy it in the memory. This particular input is not important. I'm not going to copy it, right? So you don't know what is really happening inside a neural network, but you have the feeling that this functionality is going to somehow capture the idea that you had, right? Everybody's clear? So this is what we call it gate, right? And you compute this gate, gamma, at time t. Now what you do with this gamma, you get this gamma, you multiply it to your memory, right? Exactly the same thing that we did in our dummy example. So the thing that you usually do, you get this gamma. This gamma is definitely between 0 and 1, right? Because it's coming out of the sigmoid. And then you multiply it to your memory, and you update your memory by saying, for example, moving average as we did before. And by doing that, you're somehow mimicking the same idea that I explained you in the dummy example. So I'm going to show you a bunch of examples, and you're going to get it more clearly. So we're going to see LSTM and GRU, and then you get how you can do that in practice, okay? But everybody's cool about this gate module, right? Questions on that? So gate is, again, something like, for example, you have, it's basically a fully connected layer somehow, right? X goes in and ht minus 1. Both of them go in, right? And then you get some output, right? So it's a specific form of fully connected layer, which is activated by sigmoid simply because you want to gate things. And it has a special functionality. And that is that it's going to get multiplied later to somehow gate the information that you want to pass. Now, this module, you can use it in any architecture as you want, right? So you would say, OK, here in this particular architecture, I have these features. They carry information, but I don't need all of them. I need part of them. So maybe I compute a gate, and I multiply it. You can always do it. We're going to see those examples, and you get the idea how you can design it. But you can, again, come up with your own gated architecture, exactly like convolutional architecture, fully connected architecture. It's your choice, right? Now, there are famous gated architectures. One of them is gated recurrent unit, GRU. The other one, which is the simpler one, the other one is LSTM, long short-term memory architecture. So as I told you last time, LSTM was actually the older guy. So it's like, I put the papers for you on the course page if you want to take a look. This guy was 1997. So Hochreiter and Schmidhuber. Hochreiter at that point was a master's student. He is now a very well-known professor in computer science. At that point, he just did his master thesis, and he proposed this architecture in 1997. It's not long after L-man architecture, right? A few years after L-man architecture. But then they started to somehow understand its functionality and its efficiency somewhere around 2014. And this is when this gated GRU paper was proposed. Like, people say, oh, we can do gating, and this is going to be efficient. And the first language models started to really be functional were implemented by LSTM, because this was the only architecture efficiently could get trained when you have a sequence model at that point of time, before transformers. So now, what I want to do, I want to just give you the idea of gated architecture. Now, in order to just, I mean, this is typical that we have special diagrams when we want to just present a gated architecture or any recurrent architecture. And I'm going to just show you those diagrams. In order to have a simple practice, let's just start with the basic RNN. And by basic RNN, I simply mean the L-man architecture without any gating. Okay? So you basically have an L-man architecture. You get the information at every time. You get also the memory from the previous time, the hidden state, and you process it into a new hidden state, right? So this is the architecture that you have. You have your initial hidden state, so you start with H0. You can potentially learn it. We talked about this, but it's not important. But every single time, you are going to compute one new hidden state from your previous hidden state and your input. And also, you are going to get some outputs, right? So the key point here, though, is that you are just caring about your hidden state, right? Because at every single time, the output is just computed normally from the hidden state, right? And you might be interested in processing further. Maybe you would say just one layer is not enough, right? I want to make it deeper, right? It's okay. You get this H, and then you give it to another layer, right? You might do it multiple times. But the key point here is that the one which has time connection is this hidden state, right? So the way that we usually show this in a diagram is this way. So this is the way that we used up to this point to do. So we said like ht minus 1 from previous time it comes in, and then I have xt. Then both of them go inside this particular component. This is, for example, a fully connected layer. It could be a convolutional layer, anything. And then at the output, you are going to get a hidden state, right? That hidden state is the important thing, right? So you can pass it up, right? By up, I mean to the next layer, right? That layer could directly compute you the output. Maybe that layer wants to compute another hidden feature, right? It gets ht, is compute another h prime t, right? And then after getting h prime t, now you want to process, right? You can do that, but we really don't care anymore from what's going up, right? Or what is happening actually in the upper layers, right? Because you do know this is a simple fully feed-forward network when you just look up, right, towards up. The thing that is now new for us is just this time connection, right, which is happening every time. Now, so we are mainly interested in this module, as I told you, because this is the guy which is just capturing the memory, the state, and the everything above it is not that much important. The key point that we want to understand is that how we're going to compute the newest state out of the hidden state that we have, and which components are going to pass to the next time instance, right? So you're at this particular time, you compute something, you pass it to the next time, right? So these are the things that we want to do. Here, what we are doing, we are only computing ht. And I'm going to show you when we get into LSTM, we compute more information every single time. We have solid state and hidden state, both of them together. And the thing that you are going to do, you're simply just doing it by one linear layer, right? Now, the diagram that you usually show is something like this one. So it might be a kind of diagram you have seen when you check online about recurrent networks, right? And I just want to give you the understanding how you can read this diagram. So if you look at this diagram, these lines that you see, right? they are carrying weights, right? So this guy is getting multiplied to some weight. This guy is also getting multiplied to some weights. Then when these lines meet, it means that you are just adding up, right? This is going to simplify the notation significantly. So this point here, it means that you got ht minus 1, right? You multiply it with a bunch of weights. These are the memory weights, right? And then you have your input xt is also getting multiplied with a bunch of weights. This is the input weight. They are adding up together. They are here, right? And now after this, they are going to pass through this tan H. This is the activation, right? This is what you get as your next hidden state, correct? This is exactly what we did here, right? It's the same thing. These guys go in. These guys go in. Each of them gets multiplied with its own weight. They add up. After adding them up, you just activate them, right? And we use tan H. As we said, tan H is a better option. Experimentally, we have found it for memory purposes, like reducing the vanishing gradient behavior. So that guy is just simply the same thing as I told you. It somehow tells you what is happening inside that block, right? And now, that guy you see at the output, well, this is the important thing, because this is the guy which is capturing the memory, right? Now, if you want to really finish up everything so you can get this guy, give it to one layer, it's going to compute you the output, right? This is the thing that you do in Elman network. If you want to make it deeper, maybe you get this guy, right? You just copy exactly the same thing on top of this one, and you connect HT to the input of that layer, right? So HT is going to be XT of the next layer, right? It's again the same thing, right? But the key thing here is what is happening inside this block, right? Everybody's cool? Everybody sees that here? Okay, so if you see that, now let's first start with GRU, the first gated architecture that you can think of, the very basic one. So what does it do? First of all, it's going to get one hidden state from previous time, ht minus 1, and it has xt. So these two guys are going inside one layer, right? And it's computing you one gate, right? So that gate is what we call it update gate. You're going to see why. This is update gate. Okay? Everybody's cool? Now, what is update gate? Is it a vector? Assuming x and h are vectors. Is it a vector or a scalar or a matrix or a tensor? What is it? It's a vector, right? And usually what we do, we usually put the gate to be a vector of the same dimension as the guy who we want to gate, right? Because we want every single entry to get multiplied to the corresponding entry, right? So here, this gamma that you see is a gate, is a number, is a vector of numbers between 0 and 1. And the dimension of that vector is exactly the same dimension that we want to gate. Okay? Same thing we compute here. So we have a bunch of other weights. So these weights are independent of those other weights, right? So these are new weights, fresh weights. You can train them. And what they do, they again get the same input, xt and ht minus 1. And they are computing a bunch of other gating variables. Everybody's cool? So you got these gating weights. Now the first thing that you do, you get this reset gate, and you multiply it to your memory, right? Obviously, what you can see, if the reset gate is 0, then your memory is killed, right? When your reset gate is 1, then the memory is completely maintained, right? If you have something between 0 and 1, then a part of it is maintained, part of it is lost, right? Everybody's cool? So you multiply this reset gate to your hidden state, so you somehow reset your memory. And after doing that, again, you compute the same kind of hidden state that you compute in the Elman network, right? So this H tilde is the same thing as the normal hidden state if you set your reset gate to be simply 1, right? If your reset gate is exactly 1, then you're computing exactly the same thing as before, right? Now you have this guy. What you're going to do, you're going to do the same thing we did with our dummy example. We're going to get this other gate, the update gate, and you are going to compute your memory by moving averaging using this gate, right? So you would say, whatever I had as memory, I am going to somehow get 1 minus my gate and multiply with that one. And this new memory that I have computed, I'm going to multiply it with this update gate. And you can guess why we are calling it update, right? Because when the update gate is 1, we are exactly taking the new memory. So we are updating completely. If the update gate is 0, we are not caring about what we have computed, right? We just take whatever we had from before, right? Everybody's clear? So do you see how you can build a gate and how you can use it? You can always put one gate. The dimension should match the variable that you want to gate. And you just activate by sigmoid, right? And this is going to do what you want to do. OK, now, here, this red guy, what is its dimension? Same as what? H tilde, right? Because you want to gate H tilde, right? H tilde should be the same dimension as H, of course, because you are using the same gate to gate this one as well, right? What about the reset gate? Reset gate is the green guy. The green guy should be of dimension of same thing, right? H. So your reset gate, your update gate here, your hidden state, and your actual memory, everything you are computing here, all of them are of the same dimension, right? Everybody's cool? You see that? Great. So now that you have computed your hidden state, now you can either pass it to the next layer to compute the output, or maybe you can give it to another layer to just do further processing, and then you compute the output, right? You don't really care about that. Questions? So you got how you are doing the gating, right? OK, now how we can show it in the diagram, this is going to be, yeah.
The whole point of gating is just because you have limited memory, you just pay attention to those features or
right.
That I don't know, that contribute towards classifying or reducing the loss or whatever.
Right.
Okay.
Right.
And you just ignore the rest.
Yes, that's right. But then when you get into the attention mechanism, you do the same thing, but you don't really carry it over time. Every single time you exactly look at every other token you have in your sequence, you say which one I should pay attention, which one I shouldn't. That is transformer, right? We're going to see that in the next chapter. Right. Yes? Yes.
Right? I just don't see how those are propagated into the current HT through this.
Yes, because what you can do if you set this gating to be 0, right? This the update gate. If you set it to be 0, then what you're going to get is that every single time you get your previous time memory, right? So if in some sequential times you have every time your gate to be 0, every time you're just copying your previous memory, you don't care about your actual memory, right? So update gate is exactly doing what we had in the example.
So every time you're just copying the
Previous memory.
without considering what's currently.
Yes. Like your previous memory is Julia at time, say, 1, right? So you put the gate at time 1 to be 1, right? And when it's 1, you don't care about what you had at time 0. At time 1, you're going to get Julia into your memory, right?
Yes.
And then in the next time 2, you are going to set the gate to be 0. This means that whatever you computed at time 2, you don't care. You copy the memory from time 1. And your memory at time 1 was Julia, right? So you are going to keep it. And as you go on in time, if you always set the gate to be 0, then you always keep Julia in the memory, regardless of what you are computing at this time. So you do the computation at the end of the day. That's obvious, because every time you are going to see what is your actual memory, but whether you want it or not, that is something that is decided by your gate, right? Yeah. Make sense? Yeah. OK. So now, if you want to think of that one as a block, then you can think of this architecture. Now, this architecture might sound a bit, messy and too much. So maybe we can break it down one by one. So we are getting our previous memory, we're getting our input, and we compute this gate, right? That gate is a number between 0 and 1. This is going to tell us how much we should update, right? This is the update gate. The next thing is our reset gate. So again, we get our previous memory or new input, and we compute another gate, right? This gate and this gate are computed with independent weights, right? They have their own weights. And you compute this one. For example, this guy could be 1. This guy could be 0, right? There's no reason for them to be the same, right? It's true that they are computed from the same input, but they are computed with different weights, right? So there are different modules, practically. Now, you get this guy and this guy. You have all the gates that you want. Now, the next thing that you're going to do, you're going to get your input, and you first gate this guy, right? You're going to gate this guy with the reset gate. It's going to tell you whether you really want to have the previous guy being there or not, right? The memory that you want to compute at this time, whether you want this to be completely reset, completely new, only from the input, or you want it to have a bit of information from previous time as well, right? So that is what this gate is going to do for you, right? So you're going to get the previous time. It gates it. If you put it 0, then you don't get anything from previous time. If you have it 1, you get everything from previous time. And then you combine it with the information you collected from this time. You also activate it, right? You pass it through 10H. You get your H tilde. This H tilde is the actual information, the information you are computing for this particular time, right? Now, if you want to think about this gate, how does it do? Let's assume that this gate is perfectly trained, right? And then you are reading a sentence, right? You're at the previous sentence is over. Now you start with a new sentence, right? And this sentence has to do nothing with the previous sentence. What's going to happen? You have a memory from previous sentence, right? But you don't need it, correct? Because it's a new sentence, right? So you're going to reset your memory. You say, whatever that guy was, I don't care about that, right? That is going to be 0. And then you're going to compute only the information from your first word in the sentence, right? But now, the next question is that, OK, I computed the information of this word, right? By paying attention to whether I need the information from previous words or not. But then the next question is that at the end of the day, I am going to use this information for some specific task, right? Maybe I want to classify the whole text or something. Do I need that information at all, right? The information in this particular word, right? Then the next thing is this guy, right? The update gate. The update gate is going to decide for you that one. So what it does, it's going to get multiplied with this new information that you have computed, right? It will say that it's correct that you have started with a new sentence, but maybe the first word is simply I, right? And this I is carrying not too much information, so you actually can ignore it, right? Don't put it in the memory. So you put the update gate to be 0. I don't need anything from you, right? And then you are going to still carry information from the previous time, right? Because the previous sentence, the complete previous sentence, was the important thing that you need at the end of the day, right? So this update gate is going to get multiplied with your actual memory. 1 minus that guy is getting multiplied with the previous memory that you computed. And this whole thing add up to just compute your next memory, right? Everybody's cool? And this is going to be this whole architecture that you have, right? Here is the update gate. Here is the reset gate. And everything adds up to compute your next memory component, next hidden state, right? You get this hidden state, you again pass it through the same architecture, right? Questions? Yeah.
Does this generalize well for natural language processing?
Well, LSTM itself used to generalize better. Yes, that one definitely works. The point here is that it can capture some important information in the text. Again, the memory is going to be limited. Of course, it cannot go forever. Even if you think about the transformers, at the end of the day, they also have some limited memory. But the memory that they have is far beyond the capacity that we need or we expect. So this is why we are very impressed by the performance. But at the end of the day, they again going to have a limited, finite memory, right? That finite number could be huge, but this is still limited. Whether this is going to generalize, GRU was more of kind of, toy example that people started to understand how gating works or how efficiently they can train a recurrent network. LSTM actually works, right? And like, as I said, like the first generation of language models were built using LSTM. And the machine translators, neural machine translator, they were all built initially by LSTM. And after 2017, when transformer was out and people see that this is very efficient in terms of computation, in terms of memory, then they switched to transformer completely. Nowadays, most of things are being done by transformer. But that one actually captures. You can simply do that. And if you, for example, want to do simple sentiment analysis, this one can do it, really. Yes.
But what if that sentence is related to the new sentence is related to the previous sentence? I'm like, how does it tell when the previous sentence is relevant and when it's not?
Yeah, at the end of the day, it's going to go over a large corpus of data, right? And this data is somehow labeled, right? So it's going to get trained, and through training, you're going to start understanding, right? So you're going to see that some tokens are important, some tokens are less important, and then gradually you're going to get that, right? But how exactly that happens is the magic behind all of those calculations that we do not understand, right? We always understand things at this level. When it goes deep inside, what is happening really, we don't see it. But how you can explain it, like you have a text, and this neural network is going on this one, right? Gradually, you're going to understand that, okay, there are some pronouns that are important to pay attention to. Prepositions, probably I can drop. They are not very important. Maybe there are some, like the conjugation of the verb is important, right? Things like that I should pay attention to. So how does it learn it? Basically the weights that you have here, right? So they are going to somehow, if you accept the connectionist form of thinking about intelligence, then supposedly our brain is doing the same thing. Like there is some connection between neurons. And when you learn something, some of them are just increasing the threshold, so they are not sending any signals. Some of them are really sending signals. Well, is it really what's happening inside our brain? We cannot say. So, but yeah, supposedly it's the same. I mean, at least people strongly believe up to this point that this is the case, and this is what is happening here as well, right? Yes.
So is there any reason why we set the gate value to be between 0 and 1? Can we set it either 0 or 1?
This is, yeah, you can do that, but that is not a good idea. Because you could potentially kill information, right?
Eliminate completely the other one.
That is not a good idea. I mean, there are, two reasons. One of them is just simply because if you put it 0 or 1, then this means you are going to activate by a step function, right? And by a step function, you just lose gradients, right? There's one thing. But the second thing is that you don't want to kill information, right? You want a tiny bit of information to pass, right? And even though it's very small, it could carry something for you. So it's better that you keep it always sigmoid. So deviating from sigmoid is not a good idea, really. No. Questions? Everybody's cool? So now, if you just use GRU, what's going to happen? Well, your first word, for example, first token goes inside GRU. You have your initial hidden state. It's going to compute a new hidden state, right? Now, you can give that hidden state to one layer to compute the output for you. For example, you want to classify that single word inside the sentence. Whether this is a verb, adjective, I don't know, noun, then this is going to give you the class, right? Then you carry this information, you give it to the next guy, right? And then this guy is going to the next time. The next input, next token goes in. You have your previous hidden state. You compute your next hidden state, right? You keep on going like this in time, right? As it's going to process the sequence completely. Okay. And inside every single of these GRUs is exactly the same diagram I showed you, right? So that you compute every time 2 gates. Those gates get multiplied with the corresponding memory components. They just get added up, and then finally that thing comes out of your GRU, right? Okay, now, if you want to do backward pass on GRU, like you did the forward pass, so you passed all the information through this, you computed all the outputs. Now how you're going to do the training, you don't do any magic. It's just simply backpropagation, right? But you need to do it over time. And since you are doing gating, that gating might help you to improve, right? That might help you to get less vanishing gradients. So the thing that you can do, for instance, say I want to compute the gradient with respect to the weight of the update gate, the one which is getting multiplied with the previous hidden state, right? And don't worry, I'm not going to compute it completely, I promise. It's just one slide, I guess. It's just one slide. I just want to show you, I mean, you can always do backpropagation, right? So it's very important. You can always do backpropagation. To the current state of the art that we have, we must do backpropagation to be able to train, right? So now we can, I want to just compute the gradient with respect to this one, so obviously I first compute the gradient of the loss with respect to my output. Then I start from my output, right? I would say, okay, the gradient with respect to the weight that I want to do is the gradient with respect to output times the gradient of the output with respect to that weight, right? And how does that weight comes? Well, that output is coming out of one hidden state, right? And that hidden state is multiplied with some other weights and then activated, right? So if I want to compute the gradient, then I would say the gradient with respect to weight is the gradient with respect to the hidden state that I have here times the gradient of the hidden state with respect to weights, right? That I want. And the weight that I'm right now targeting is something inside the gauge, right? So it's not this weight, right? If I wanted to compute with respect to that weight, I stop here, right? If I want to go further, I can write down the chain rule more and more, right? So what is the next guy? Okay, this hidden state is depending on my gate in this form, right? Hidden state is computed in terms of this gate, the previous hidden state, and my actual memory, right? Correct? Now I want to compute the gradient with respect to particular way that I want. I start writing things down, right? I would say, well, I have the gradient with respect to the gate times the gradient of the gate with respect to my weight, right? Plus the gradient with respect to previous hidden state times gradient of the previous hidden state, right? Is there anything more? Well, I have another actual memory, right? I can compute with respect to that one as well, right? Anything that you have in your layer, which is depending on the previous time or depending on the gate, on the weights directly or indirectly, then you should include it. And you can keep on going like this, right? You end up at some point with either initial hidden state or you just terminate at some point because you're not passing any more backward. And at that point, your backpropagation is over, right? Everybody's clear? Okay, so moral of the story, definitely you can do it. And even though it looks quite complicated, but you can simply write it. It's just a messy calculation. It's nothing more than that. There is no magic going on. You don't need to know Riemannian manifold to be able to backpropagate. It's just simple chain rule, right? Just simple chain rule, the one you had in high school. Okay. Next guy, LSTM. How does the LSTM work? Actually, LSTM computes 3 gates here. So it has one forget gate, input gate, the output gate. So every single of them has its own weights computed from the input and the previous hidden state, right? Now, these hidden states are HT minus 1, as you see. But here inside LSTM, you have also one extra memory component. This is what we call it cell state. And you're going to see what does it do. So first of all, the previous hidden state comes in. The input also comes in. And then they are going to get multiplied with their own weights. Every single gate has its own weights, right? So they are independent. If you want to think about it, it's like X and H come in, and you have like in parallel different gates, right? Computed in parallel. Every single of them with its own weights, right? You can do this all of these three computations in parallel, right? Okay. Now that you have this, now you are going to compute your cell state. What is the cell state? This is essentially the same thing you compute in LMAN, right? Input, previous hidden state, you compute the cell state at this time, right? So in LMAN, what you do, you compute line 5, right? And you call it your new hidden state, right? But here, they do not call it a new hidden state. They called it cell state, right? And then they get this cell state. This is the guy that you had before. This is the guy you computed, C tilde here. Now, you have your cell state from previous time, okay? This C was also computed in previous time, right? You get your previous cell state, your new actual memory you computed, that's C tilde, and you gate both of them, right? One of them is multiplied with a forget gate. That one is telling you whether you should forget the previous cell state or not. The other one is the input gate, right? It's going to tell you whether this new memory component you computed at this time, you need to keep it or not, right? Now that you have computed this guy, this is cell state still, right? This is not the hidden state. And how you compute the hidden state? You simply just gate the cell state to get your hidden state, right? Everybody see that? So you gate it once again. And one trick that they did in the paper initially experimentally, and they found that it was efficient, was that you do one extra activation here. Why? Probably is again because of vanishing gradient, but anyways, when they again get this cell state, they first activate it and then gate it. So they do not directly gate it, okay? But it turns out to work better. Questions? So what is happening? 3 gates computed in parallel. Then you compute a memory component, that is the cell state. You gate it using your gates to just somehow mix it with your previous cell state. And then whatever you computed, you again gate it at the output, right? Before you compute your new hidden state, right? Now, one thing that you see here is that the cell state is somehow remains inside your block, right? It doesn't go up. If you want to compute the output, you essentially just compute it out of your hidden state, right? Everybody's cool? Questions? Yes?
Why does, like sigmoid is less than 1, right?
Right.
Why does activating help reduce vanishing gradient?
Activating, this does nothing, it's not necessarily sigma, actually it's tanh.
Okay.
It does nothing with the gating, it's not a gate.
No, but why does it help reduce vanishing gradient?
I think like if you have tanh, like in the assignment I gave you this dummy example, and then this tanh has this expansion at small values, which is very close to 1. And then this is going to help better than having the small values themselves. So it could help, but this was just simply experimental. So you can come up with your own gated architecture. People have done this. Not that like they got like too much benefit, but sometimes for some application you obviously see that, well, it's better that I do another gating here, yeah? And then you just can add it. Maybe I can do more activations. This is just, you know, experimental thing, right? You just try over and over and you see which one works. But nowadays it doesn't make sense anymore, right? It was something like in 2000, right? Yeah. Questions? No question? Okay, so here is the overall architecture of LSTM. As you see, you have 3 gates: forget gate, input gate, the output gate, and every single of them is just gating that one particular part of your memory calculation. What you get your previous cell state, you get your hidden state, right? And then this cell state is going to remain here, right? It just passes to the next time, whereas the hidden state, HT, is going to pass to the higher layers if you want to compute your output, right? Now, if you want to think about this again, you could say I have my previous hidden state, I have my input, right? And I compute first one cell state, right? This is the actual cell state that you have, right? Then you get your two gates. One of them is the forget gate, which is just gating the previous cell state. The other one is the input gate, which is gating the actual memory you computed. So this input gate is gating this guy, right? Whereas the forget gate is gating the previous cell state that you had. Now that you have this one, then essentially you have computed your new cell state, right? But the extra thing that you do is that you again compute an output gate, and you would say, okay, this output gate that I computed is going to tell me how much of the information I computed at this time is going to pass as a hidden state for the output and also to the next time. So this is the extra hidden state that you compute, right? This is the guy. And then if you want to just calculate your output, HT is going to compute your YT, for example, right? Questions? No question? Okay, now, always when you have a gated architecture, you can always play around with the gates to see what is the functionality of every single gate. For example, if you set the forget gate to be 0, what does it mean? It means that this cell state from previous time is going to get killed, right? So it's going to make your information only depend on the actual memory you computed at that particular time, right? This is roughly, I mean, when this forget gate is 0 and input gate is 1, that CT is essentially what you compute in the L-man architecture, right? It's the same thing as before, correct? Now, input gate is essentially, if you set it 1, this is going to just pass every information you computed at this time to the cell state. If you put it 0, again, it's going to kill whatever you computed at this time, right? And then you also have the output gate. The output gate, again, if you set it to be 0, then the cell state is going to just cut out, right? Nothing going to go out, right? You're going to kill everything, a single output. I don't want anything goes out, right? And if you set it 1, then everything you compute as cell state is going to get out, right? Everybody's cool? Questions? No question? So same thing as GRU. So you start with one hidden state, initial hidden state. Your first input goes in. Your first hidden state is computed. And then you go for the next time, right? The only difference here is that every time you also compute the cell state, but you don't need cell state for the higher layers, right? You're going to just keep it for yourself for the next time that you want to compute, right? It's a kind of extra memory that you have, more, say, informative memory, which might be not very useful for your output, but it's useful for you to just carry information, right? And you just go over time like this. So the key difference here is that you have cell state. And as I said, you can come up with your own gated approach. Now, nowadays, of course, we have huge sequences. We do not really process them anymore too much with LSTM. But there are still many applications where the sequences are simple. This is an effective solution. And gating is not only showing up here in this particular application. You can use the idea of gating in many other problems. For example, if you want to make privacy, right? You don't want all the information to get out, right? Then you can use the idea of gating. And there are lots of works on that respect as well if you take a look to the literature. OK, so backpropagation on, yeah. Yes. Right. Okay. Actually, H, you are computing H. Just look at this guy. Yes, you're computing H directly from C, right? And then you cannot say that this guy is carrying 40%, that is 20%. No, I mean, it's not real. If you think about information only, not about computation and numbers, then this guy is actually have a part of, I mean, in the best case, it has all the information or a part of it, right? No, no, no worries. Yes.
Does C correspond to long-term memory and H correspond to?
Somehow, yes, yes. That is what you want to know right now for deciding. So you don't want to have misleading information, but you can carry longer information using the solid state. That's correct, right? Yeah. But it's not like you have long-term and short-term, so it's long, short-term memory, right? You compute short-term memory, but you keep it for a long time, right? So that is the idea. But the idea is the same thing I told you, right? So your memory is able to just carry information about one part of the sentence, for example, or some specific parts of the sentence. That is a short size memory, right? But you want to carry it for a long time. The idea of gating was for that. Yeah. Yeah, go ahead. No? No?
I did have a question, but I didn't pick up my hand.
Okay, okay.
No, I was just going to ask, you said GRU is more modern, and LSTM is older.
Yes.
So what they realized that South State was unnecessary, and then they removed
No, actually, they didn't see that this is unnecessary. That one is simply.
GRU,
GRU is simpler.
but relative performance-wise.
Not necessarily. I mean, LSTM is the one which is used in practice, mostly. So you can do GRU, but GRU, as I said, is just more of a toy example.
So it's modern, but it's for simplification.
Right. Yeah. Yes.
And which one has more capacity?
Of course, this one, because it has more gates, right? Yeah, it's gonna give you more capability to pay attention to specific parts, right? In practice, LSTM was the one which was used in most, like before 2017, language models. You can build one language model using a GRU, that's simple, and it can do just very basic stuff, but if you want to make it a bit more serious than LSTM. Questions? No question. Okay, so how we can backpropagate over this one? Well, same thing again. I'm sorry by being so obsessed with that one, but this is the only thing that makes the whole training to work. And yeah, just start computing, writing down chain rule, right? Chain rule with respect to output, then from output you get to the hidden state, then from the hidden state you get to any gates that you want, right? And of course, the solid state somewhere shows up in between, and then you are supposed to compute the gradient with respect to that one as well. You can go on and write things down, and then you get into a set of equations, which are the update rules for backpropagation through time, right? And nowadays, PyTorch does it for you, but old days, people, when they build this, they just write down those equations, they implement this, and they say, okay, we can now efficiently train this guy, right? Good old days, right? Yeah, that you can do this. So I'm not going to open it up because it's going to get a bit messy, but the key point is that you're self-confident. You can do it, right? Always. Okay, yeah, if you have spare time, just try writing that down, right? Okay, now, just few extra points on the recurrent architectures. Well, people, when they started to work with recurrent architectures, initially RNN was not working. So it was a good theory, not working. Then after seeing LSTM, I mean, they started to somehow understand what it's doing. It was somehow left for a decade or 15 years, up to the point that people again got back to it and then started to use it because they had more memory, and somehow on the vision tasks, neural network started to do something. So they said maybe we were impatient. Maybe we could get back to the sequence processing and see whether we can do things. So they started to do that, and LSTM was the first guy who started to magically work, and it was because of gating. Now, after doing that, people started to do a lot of tasks on the sequences. And one of the things that they noted was that you do not always need to start from the very beginning of the sequence, right? So it's not that the information that you have is always causal, right? It's always before in time, right? For instance, let me just give you some example. Say you want to fill out this sentence, right? the color blank that many people assume is the color of sun. So what you should write there? A test. Yellow, right? The color yellow that many people assume is the color of the sun, right? Sun is not yellow, right? You know that. It's a complete spectrum, right? Anyways, just so here you can answer this question because of sun, right? So the information that you need to complete is in the future, right? But you have the whole sentence, right? Now you want your neural network to go over it and give you the answer, right? So what you can do, maybe you start like instead of starting from beginning, you can start from the end, right? Or maybe you can do both directions, right? That was the idea that people started to say maybe we can process the sequences bidirectional. Well, when we get into attention, we naturally do that. How we can do that? But in this case, how we can do that, we can start from here and then process the hidden state, compute hidden state for the next time. And also we start with another hidden state, starting from the end of the sentence, for example. And then we just go back, right? And every time we compute that one as well. Now, this is the kind of idea that you can do, right? So you would say, I have the previous time hidden state, right? I have my input. I compute the hidden state at this time, right? I also have another hidden state, which is carried by the other, for example, LSTM or other network. And that guy is giving me the future hidden state, right? And then I get that guy with my input. I compute my current hidden state, my current second hidden state, right? And then I process HT and H prime T both together to compute my output, right? A part of information is in the past, a part of information is in the future, and I combine both of them, right? So you can compute it this way. So you start from H0 here, right? And then you go over your sequence, right? And also in the other guy, you start from HT plus 1, right? So there is one initial state there as well, which is like your last token next, right? You start from that one, you just go backward, right? And then you get at one particular time. At that particular time, you have two different hidden states. One of them is the future hidden state. The other one is the past hidden state, and you combine both of them, right? So you get both of them. You do some sort of merging here, and then you compute the output. Everybody's clear? This is what we call it bidirectional sequence processing or bidirectional RNN. Now, how can we do the merging? As you want. Okay? You can cascade them. You can concatenate them. You can add them. You can multiply them. I think you get this idea that whatever you do, any mathematical operation, you do want that. At the end of the day, if you just leave a bunch of weights there, or if you do it like not very harshly to kill anything, then they are going to carry information, right? So the layers are going to take care of that for you, right? So you can do as you want. Just the important thing is that both of these hidden states are there when you are computing your output. So yeah, you can do it by GRU. You can do it by LSTM. So it's nothing specific. If you are doing LSTM, of course, you have solid state, which is going to remain in every single LSTM. But that's not a very complicated thing, right? You can do your merging. So all of them are the same. In general, you can do this with any RNN architecture. And how you can do this merging, as I told you, you can do anything that you want, right? Concatenation is a typical thing. Like you get your first hidden state, the second hidden state is below it, and this whole thing is your new hidden state, right? And then you process that one. This is a typical thing, but you can also add them up, right? Yes?
I have only one output for the whole sequence. Does this make sense or not?
Sorry, I didn't get you.
If you had only one output for the whole sequence.
One output for the whole sequence, like sentiment analysis.
But you don't need to do this, right?
Well, yes, you can do it still. It's no problem.
But this does help or not?
It could potentially help. It depends on your application, right? So, for example, in the example I gave you, it definitely helps. But like you can start from beginning, get to this point. and then from the very end, somebody else, some other network computes you something, and then you combine them, right? You can do it, yeah, but it depends on the problem. If the problem is super simple, then one hidden state could be enough, right? But the key point is that you're changing the time direction, right? So the memory is not only about like you're losing or forgetting memory, it's the kind of way that the memory is computed, right? It might be that the future information is somehow helping. For instance, in some languages, you write from right to left, right? The text. But the numbers are from left to right, right? This is a different structure as the languages where people write the text and the numbers the same direction, right? It could help, right? Questions? Okay, no question. Now, yeah, RNN, if you want to really implement it, like old days, you might get this very challenging exercise that you go home and implement LMAN, which can get trained because it was hard to train. And then you use PyTorch and see whether it's working as well or not, because PyTorch is somehow able to do it more efficiently. But nowadays, you don't really need to do that. So you can simply access LSTM, GRU, RNN, whatever you want. The basic RNN, that RNN, when you call it, is basically the LMAN architecture if you set the number of layers to be 1. But the other architectures are going to be like exactly the ones I told you. You can play with the layers. Everything is OK. How, if you are doing bidirectional, how you can do it, you can have both hidden states concatenated, as I told you, or you can average them out. One thing is that when you call them in PyTorch, you have also this option to set it bidirectional, right? And it's automatically make 2 LSTM, for example, for you, and pass them in 2 different directions on your text. And it's going to give you both hidden states. And then you're free to do whatever you want with those hidden states.